Hi there, welcome to today's lecture. Today we're going to be talking about those inner pieces inside the atom, the subatomic particles, the proton, the neutron, the electron, and kind of give you an idea of what those little particles are like and how we can look at a periodic table and distinguish what some of those values are. Okay, so as we get going here today, this is 4.2, and it's just the first part. We'll have another part of this lecture later on. Our objective today: let's look at the protons, neutrons, and electrons and identify their properties like the charge, relative mass, and location. We're going to define the atomic number and mass number. A lot of little terms here today. They're a little bit different from each other. We want to be able to distinguish those. And then we want to determine the number of protons, neutrons, and electrons in the neutral atom of an element. So we're going to throw something up as an example from the periodic table and see if you can figure it out. And then we're going to describe the role of isotopes in calculating something called the atomic mass and the average atomic mass. And you're going to learn about those things. So let's start out by asking this question. What determines if an atom is harmless oxygen or poisonous arsenic? Well, I'll tell you what it is. It's the number of protons. Now, you may have had that figured out. It doesn't necessarily have to make sense how one little extra proton all of a sudden makes something go from gold to mercury. It's pretty amazing stuff. But we figured out what it is. We don't necessarily understand why it is all the time, but we can at least tell you, hey, the reason 79 gold is a little bit different than 80 mercury is because of that one little proton, okay? So what are subatomic particles? They're the particles that are smaller than an atom, right? Sub, beneath, right? Atomic, sub, beneath atomic, the smaller than the atomic. Three primary subatomic particles are protons, neutrons, and electrons. What do you know about each one? Well, we know that the protons are positively charged and they have a particular mass. The neutrons have a very similar mass. They're slightly heavier than a proton, but they have no charge, okay? They have no charge. And then the electrons are really small compared to the protons and neutrons, about 1,840 times smaller. And they have much less, we said they're much less mass, and they have a negative charge. And that charge is exactly opposite but equal to the charge of the protons. So the charge of a proton and the charge of an electron exactly balance each other out. It's kind of cool. All right, so let's look at that. If I were to, and you don't have to write this chart down or anything, but if we were to kind of summarize the charges, protons +1, electrons -1, neutrons nothing. These are their masses. Now notice how small these things are. 1.67 times 10 to the -27th kilograms. That's a very, very, very small amount. Over here, we've got 9.11 times 10 to the -31st. Now, you'll notice this is a mass. It does have mass. Electrons have mass. But when we talk about the masses of electrons, they're so small compared to the masses of protons and neutrons that they're pretty much negligible in most all cases. All right, so location in the atom, obviously the protons and neutrons are in the nucleus, and we've talked about just in the last lecture how the electrons are outside the nucleus. All right, so let's talk about what these things would be symbolized as, and let's talk about a relative mass. Now, when scientists came up with, talking about masses of atoms, they didn't want to use that 1.67 times 10 to the -27th number over and over and over again, right? That's kind of a mouthful. So they said, you know what? Let's come up with something that is a relative mass. Now, this would be like if, we had a classroom of students here, and I looked at Sam over there, and I said, Sam, you are going to be the standard for this room, and we're going to take your weight, and everybody else in this room is going to be measured according to your standard. And so if we said, hey, that's one Sam, because that's Sam, then if I looked at Lily and I said, hey, Lily, you're 1.5 Sams, or you're 0.4 Sams, you're, quarter of a Sam. Like if we took everybody in this room and we figured out what their masses were relative to Sam, those would be relative masses. Now that's what they did with the atom. They came up with relative masses. And so we're going to talk about the relative mass of the proton, neutron, and electron. And then we want to talk about what is the function? What do these particles do in the atom? Because each of them is actually giving some sort of a function. And so let's talk about, first of all, the proton. We use that symbol. It's a P with a little plus on it. Its relative mass is 1. Now, we use this unit AMU. It's atomic mass unit, and you'll learn a little bit more about that in a bit. And then what is the function? Well, it gives us identity. It tells us what the atom is. Every single proton that we add into an atom is going to change the identity just a little bit. And now our neutron has an N with a little 0 on top. That's its symbol. and its relative mass is 1 AMU. And what is the function? It stabilizes the nucleus. In fact, the larger the atom is, the more neutrons you're going to find in the atom. And so bigger and bigger and bigger atoms become a little bit less stable. And so as you add neutrons, it actually becomes a little bit more stable. And then our electron, negative, even a little negative sign on top, and then it's 1/1840th of an AMU, pretty much nothing. It's kind of like what like a little dime would be on the top of a gallon jug of milk. It just isn't going to measure up to much at all. And then what is the function? Well, it's going to be forming bonds with other atoms to make molecules. It gives the reactive properties of the elements. Okay, so the number of electrons in the valence shell will determine the reactive properties of those elements. Is it reactive? Is it not? How does it react in certain situations? Okay, so let's practice some of these. And again, this will be a great place for you to read and then pause it and practice. Ready? Pause it and practice, and we're back. Okay, if you wanted to find the mass of an atom, which two particles would contribute the most mass? The protons and the neutrons. True or false? The mass of a proton is equal to about 2,000 electrons. Yeah, that's about right. Okay, it's actually 1,840. True or false? To balance the electrical charge in an atom, every proton must be matched with 2,000 electrons. No, 1-on-1. It's a 1-to-1 ratio for charge. True or false? The nucleus fills up most of the volume of an atom. Right? We learned it last lecture. What is it that makes up most of the volume? Nothing. Empty space makes up most of the volume of an atom. All right. So let's look at the total charge of the atom. Remember that the total charge of the atom is the sum of the charges of all the subatomic particles. Well, the neutrons always have a 0 charge. So we just look at the number of protons and electrons to determine the charge of the overall atom. If you have the same number of protons as electrons, then the charge of your atom is 0. And this is what we're going to have with all of the elements that we refer to on the periodic table when we talk about them in their neutral state or their natural state, okay, that they're going to have a same charge of protons and neutrons, so there'll be a neutral atom, okay? If it's not a neutral atom, we'll tell you that it's an ion, and we'll give you a little charge symbol on top of it. So that was for lithium. For argon, same kind of thing. I'd have to have 18 electrons down here and then 18 protons up here to give it a 0. The charge of the 20 neutrons, that's a 0. There's no charge. Even though there's 20 neutrons, there's no charge there, okay? It looks like it says 20. It doesn't say 20. It says 0, all right? 0 is the charge of 20 neutrons. That's an error. All right, let's go on. All right, so our atomic number. Now, notice we use the symbol Z. The atomic number is the number of protons in an atom. And we use the symbol Z to tell us how many protons we have. And so if we say, hey, it's Z number is, you would tell me the number of protons. Okay? The number of protons in a particular element does not change. If I were to change the number of protons, it would no longer be that element. It would be a different element, right? So, again, remember, protons and electrons are going to be equal in a neutral atom. And we can find the number of protons on the periodic table. So for instance, for fluorine, look up fluorine on the periodic table. You can open up your books and you'll see fluorine on the periodic table, or you can look at the periodic table that I've given you in the on your website in the Google Classroom, and you can look there as well. Your periodic table is found in the back of your text, okay? So you're going to see it on that last back page. Now, you may not have that back page anymore, but hopefully you do. If not, you can look at the periodic table that you see in your classroom, okay? It'll be on the resources section of the materials. All right, so, so look at fluorine, and you find fluorine, it's number 9 on that periodic table, which means that it has 9 protons. That number up in the top right-hand corner, or on some periodic tables it might be in the middle, that number is going to be the number of protons that the element has, okay? And so how many electrons must it have? 9, right? Same number of protons as electrons if it's any of the elements that are on that periodic table. How many neutrons does it have? Well, you can't look at a typical periodic table and tell how many neutrons it has because there's no mass number on a periodic table, okay? And we'll talk about that here in a second. All right, so how do I calculate protons and electrons in a neutral atom? Well, nitrogen, find it on the periodic table. It's number 7. Therefore, it has 7 protons, 7 electrons, right? You're going to pause it and practice the next 2. Pause it and practice. Go. All right, and you're back. Bromine, number 35 in the periodic table, 35 protons, 35 electrons. Calcium, number 20 on the periodic table, 20 protons, 20 electrons. All right, so let's look at mass number. Now, mass number is the value A, okay? So remember, atomic number was Z, mass number is A. And mass number is number of protons and number of neutrons added together. And again, you cannot find this on the periodic table. Mass number is always a whole number because we have whole numbers of protons and neutrons in any atom, right? And so if I were to look at this nucleus here and I count up my number of whites, 1, 2, 3, 4, 5, and I count up my number of reds, 1, 2, 3, 4, 5, now I know that I've got a mass number of 10. Now, can you tell me what element this is if that's showing all of the subatomic particles? 5 protons is going to be what? Oh, yeah, boron. So this is boron, and it's got 5 protons, 5 neutrons. Its atomic number, its Z, is 5, okay? And its mass number, A, is 10. Now, if I were to look at chlorine, there's 2 ways that I write symbols for the mass numbers. I can either do it in a hyphenated form. This is an isotope of chlorine. It's a type of chlorine that has 35 total as its mass number. And so I say chlorine 35 is the type of chlorine I'm talking about here. And that's one way of doing it. Another way of doing it is like this, with the 35 on top of the 17. Now, what is that number 17? When you're looking at the 17, that number is the number of protons. So if you look at chlorine, find it on the periodic table, you're going to see it has 17 protons. So 17 is the number of protons. So I've got 35 of my total particles, my protons and neutrons, and I've got 17 protons. So if I want to know how many neutrons I have, now I can figure out how many neutrons I have because I've been given the mass number. All I have to do is subtract 17 from 35, and I realize I have 18 neutrons. So that's how you figure out the number of neutrons when you have the mass number. So let's look at this. This is a good practice. If I have atomic number of beryllium, let's fill these in. But I want you to go ahead and pause and practice real quick. Pause it, practice, and you're back. So good to have you back. All right, my atomic number of beryllium is 9. My hydrogen, sorry, that was silly. My atomic number of beryllium, I got to go to the periodic table, right? And I got to find Be on the periodic table. And I see that beryllium is 4. I was just testing you there. My hydrogen is 1, and my hydrogen is 1. What? There's a 2 there. Remember, hydrogen is always going to have the same number of protons. So I just look on the periodic table, see how many protons it has when I look for hydrogen, and it's the number 1, and that's what the value is going to be. My mass number is 9. Remember, this number here at the end in this hyphenated form is the mass number, so I know what my mass numbers are. My number of protons is the same as my atomic number, so I've got to have 4, 1, and 1. My number of electrons has got to be the same as my number of protons in a neutral atom, so I'm still 4, 1, and 1. And my number of neutrons, now I can do a subtraction. 9 minus 4 is 5, okay? 1 minus 1 is 0. 2 minus 1 is 1. So now you know how many neutrons each of those have. Now, there's a little story here at the bottom, a little bit of interesting information. This hydrogen here is called deuterium. And deuterium is a type of water that you really couldn't tell by appearance was different from tap water. It is a little bit heavy, as we actually call it heavy water, and it weighs just a little bit more than regular tap water. Basically, about 1 drop out of every 6,000 drops you drink would be equivalent to how much heavy water you might drink. And if you had only heavy water, it would be bad for you. Seeds don't sprout. Mice become dehydrated. It's actually kind of interesting. It's a really cool story. There were a couple scientists, and I forget their names now, but one of them had been doing experiments with these cyclotrons for years. And in this little experiment with cyclotrons, he'd been collecting heavy water that was a byproduct of these little nuclear experiments. And so he had this, decent collection of heavy water. Basically, it was a bottle of it, and it took a long time to collect all that. And one of the scientists in his lab was like, listen, I want to try something. I want to see what's going to happen to this mouse when I give it heavy water. And so he gave the mouse, he basically borrowed the water. He's like, I just want to borrow it. Can I borrow it for now? And so he took the water, he poured it into the little mouse drinking thing. And, the mouse is drinking it. I was like, okay, this should be interesting. He goes home and he comes back the next day. I think it was the next day. Maybe it was longer. I don't know how this happens in a day. But he comes back and the next day, the mouse is dead. The water is gone. Now, this water took years to collect. You can imagine what he's doing, panicking that his colleague is going to just kill him, right? What happened? Well, the mouse was drinking water and getting nothing out of it. And he was peeing it out, but there was no actual nourishment. It wasn't going into his cells and doing the stuff that, water needs to do in your cells. And so this mouse just kept drinking and drinking and drinking and wasn't getting any water into his cells. And so his body just kept telling him, you're thirsty, you're thirsty, you're thirsty. Keep drinking, keep drinking, keep drinking. Kept drinking, kept peeing, and he died of dehydration. Apparently it was the next day, from what I remember on that story. It's crazy that could happen in a day. But anyway, you can imagine that those two scientists might not have had a great relationship after that. Years of deuterium, heavy water, collected and then gone. Oh my goodness, isn't that an interesting story? Yes, Mr. Powers, it is. Yeah, I thought so too. All right, so isotopes. Now, an isotope is an atom that has a different number of neutrons. Now, all three of these are isotopes, okay? This is an isotope with 0 neutrons, isotope with 1 neutron, isotope with 2 neutrons. Isotopes basically have the same number of protons, but different numbers of neutrons. So hydrogen-1, protium, hydrogen-2, deuterium, and hydrogen-3, tritium are all isotopes of each other, okay? And there are a lot of isotopes out there. Some elements have hundreds, or 100 anyway, or more different isotopes. Okay, some of those really heavy elements have got all sorts of different numbers of neutrons, and so you can have lots and lots and lots of different types of neutrons. I think there are some that have over 100. I could be wrong on that. All right, atomic mass. Actual mass of an atom is very small, yeah? So we have to come up with, how do we come up with that mass of an atom? Well, let's do a relative mass. So just like I was talking about having so many SAMs and comparing everybody to SAM, right? Compare the masses of all atoms to that of a carbon-12 atom. So we just take carbon-12 as a standard. Like I said, we take SAM as a standard. And now, in this case, they decided to divide up carbon-12 into 12 equal pieces. Okay, SAM, don't worry, we're not going to divide you up. But we take 12 pieces of carbon-12, and we're going to say, okay, each one of those pieces is equal to 1 AMU, 1 atomic mass unit. Now, this is also called a unified atomic mass unit, so you'll see the symbol as either an AMU, or sometimes you're going to see it as a U, okay? And again, it's equal to 1/12 of the mass of a carbon-12 atom. This is about relative masses, okay? So 1 U is about the mass of 1 proton. So hydrogen-1, which had just 1 proton, is going to have a mass of 1 U. Does that make sense? So that's atomic mass. Now, let's look at the average atomic mass, because atomic mass is not the same thing as average atomic mass. Average atomic mass is a calculation of all the different types of isotopes that there are. Okay, so if I have carbon-12 and carbon-14 and carbon-13, various different types of isotopes of carbon, I'm going to take the percentage of each of those different types of carbon. I'm going to weigh them out relative to each other, and I'm going to come out with an average. That's my average atomic mass. Now, this is it's not going to be a whole number, right? Because it's going to be an average of 35 and 36. You come up with an average of 35.5. It's not a whole number, right? So these are not whole numbers. So if I have chlorine, for instance, which has 24% of the chlorine that we find in nature is chlorine-37. And 76% of the chlorine that we find in nature is chlorine-35. So if we take it, most chlorine is chlorine-35, and so this number is actually kind of close to 35, even though 24% of all chlorine we find is actually going to weigh more. 24% weighs 37 AMU, whereas 76% weighs 35 AMU. The average of those two is 35.453. Okay, so that is where we come up with average atomic mass. It's the average of all the weighted isotopes of an element. Okay, so let's practice that. Using the periodic table, again, look in your book or grab one from the section there. Determine the average atomic mass of each element listed. Now, these numbers are at the bottom. So when you look at your periodic table, look at the bottom. Okay, and it's the number that's going to be at the bottom of these. So if I look at neon, which is our first one, I come over here. I don't know if you can read this, but neon is 20.1797. Okay, so that is the average atomic mass of neon. All right, so why don't you pause it and practice? And you're back. Good to see you again. Potassium, you look at number 19. Potassium is 39.0983. Iron is number 26, and it's 55.845. Okay, so those are the average atomic masses of each of those. How does the mass of an iron atom compare to the mass of a potassium atom? Well, the mass of the iron is going to be greater than the mass of the potassium, right? Iron has 26 protons and potassium has 19 protons, and they both have a similar number of neutrons. So iron is more massive. What's the number of protons, neutrons, and electrons in potassium 39? Well, there's 19 protons. That's what that Z number is, right? Its A is 39. That's the number of neutrons. Therefore, I got to subtract the 2 to find my number of neutrons. It's got 20 neutrons. And, of course, its number of electrons is the same as the number of protons, so it's 19. Average mass of the element lithium is 6.94 U. Which isotope of lithium is the most common? Well, if it's closer to 7, that means I must have more lithium-7 than I have lithium-6 because it's an average, and the average is closer to 7. Make sense? All right. Woo! Fun stuff, right? Okay, so let's see if we know some new things now. It sure seems like we do. Protons, neutrons, and electrons are subatomic particles. Yeah, we got that. Identify their properties. Oh, yeah. Charges, right? We know the charge is positive for proton, negative for electron, neutral for neutron. Do we know its mass? Yeah, protons and neutrons are really heavy compared to the electron. Location, protons, neutrons in the middle, electrons on the outside. Yeah, man, we got this. We're smart. Define the atomic number and the mass number. Atomic number is the number of protons. The mass number is the number of protons plus the number of neutrons together. The number of protons, neutrons, and electrons in a neutral atom of an element. So if I tell you something like germanium, you're going to be like, oh, yeah, germanium. Germanium has 32 protons. And you can tell me, I won't just say germanium, will be like germanium-72 or something. And then you can tell me how many neutrons it has, 40 neutrons, and it has electrons. Oh, that's same number as the protons, so it's 32. All right. Describe the role of isotopes in the calculation of atomic mass. We have to take the average weighted amount of all the isotopes, and then we get the average atomic mass. Okay, good stuff, right? Now we know a little bit more about the inside of the atom and those different particles and some of their properties, which is the idea here. And again, why is this important to us? Well, you know, it's again helping us to understand the difference between like something like oxygen. Well, I mean, let's just go back to our regular hydrogen, right? Deuterium, the heavy water versus the not heavy water. Like just the number of neutrons in a particular atom can make a difference in our bodies to whether or not we can process it or not. Like that's pretty interesting stuff. That's pretty crazy cool stuff, and it's applicable, right? Poor mouse dead applicable. You know, when you get to some other part of your life and you're like, I wonder if this is okay. It actually might have an effect if it has a different number of neutrons, different isotopes. And we're going to talk about radioactivity later on. And radioactivity is all sorts to do with neutrons. Anyway, cool stuff. Thanks for joining me today. I hope you guys have an awesome day. Be kind to each other. God bless.